Okay, I think we can slowly start. So thank you very much to everyone for coming to this last session. If you notice there's a typo on the slide, just to wake you up. So it's a catch. And yes, this talk was not planned, so I voluntarily agreed to give this talk on what is algebraic statistics, so that maybe some of you that are new to this concept can understand a little bit what we're coming from and where are we going. So let's start with the points in common between let's say algebraic geometry and statistics. So in statistics you usually have a family of probability distributions. This can maybe sometimes be given by a parametrization, and you want to make inference with data that you collect. And of course we all know that this is very useful in many different fields of science. I listed a few of them here. But what maybe is not known to you, or maybe known but you were not aware too much of, is that many times these statistical models can be described by solutions to systems of algebraic equations. So an algebraic variety is a set of solutions to a system of polynomial equations. Okay? And in pure algebraic variety, we usually look at these solutions over the complex numbers. And when we are talking about statistics, we have to put on some restrictions on this algebraic variety. Namely, we have to request that the points that we look at are positive real numbers. Like in this case, imagine that we intersect this red curve with this triangle, which is the probability simplex. Okay, so the point is that many statistical models are in fact algebraic varieties. And this is one of the main principles that has moved algebraic statistics and our contributions. So if you want more examples of algebraic varieties, here I have a few pictures. Bernd already told us about the samosa. This is not the samosa. No, this is the elliptope. That's French candy. Okay, French candy. And also like a Valentine here. These are algebraic varieties, so these are just some examples of varieties that we see in life. And the point is that in the last years, there have been two types of advancements in algebraic geometry. On the one hand, you have theoretical advancements. That means, algebraic geometry is a very robust field of science, of mathematics. There's, theoretical understanding of many things you can do with varieties. This is at the theoretical level. But in terms of computation, with the fast development of computers, you can do many concrete calculations with algebraic varieties. So you have to combine the theoretical advancements in algebraic geometry with the computational power that is now possible. And how do we compute things in algebra and geometry? Well, we use a wide range of software that you can see here. So these, let's say, several decades ago was restricted to symbolic computation. So here I have different examples of symbolic software that can do computations for algebraic varieties, mostly using Grosvenor basis. But more recently we have packages like homotopy continuation.jl, and also some more recent packages like Oscar, who is developed, that is a software developed in Julia. And the point is that this allows us to do numerical algebraic geometry. So this is the paradigm here, is that we're using really the algebraic geometry of these objects to do numerical computations. So you can imagine that theoretical advancements with computational advancements could lead us to breakthroughs in other fields of science, and that's one of the goals of algebraic statistics when we restrict to trying to solve problems in statistics. So what's the goal of algebraic statistics? Well, we tackle problems in statistics using tools from algebraic geometry, commutative algebra, combinatorics, symbolic computation, and numerical algebraic geometry. Here I put up some pictures of things I thought were nice. And let me tell you a little bit about the connections between algebraic statistics and information geometry. So as Bernd pointed out many times during his talk, the world is toric. So I'm gonna repeat that here in the sense that discrete exponential families are toric varieties. So what is a toric variety? You can think of a toric variety in the following way. It's a set of solutions to a system of polynomial equations whose polynomials are binomials. Okay, so it's like the simplest thing you can think about. So it's nice. It's just binomials. So this is very good. Now, beyond a simple representation of the equations that define the variety, the toric geometry is very rich because you can study the geometry here, for example, of the surface you see in the simplex by studying the geometry of the associated polytope to the variety. Okay, so here the polytope associated to this variety is a square. In general, in the toric geometry world, you take a variety and you associate a polytope to it. And the geometry of the variety is governed by discrete geometric invariants of the polytope. So it's a very rich interchange of language to study the geometry of varieties. Okay, so in algebraic statistics, we study a lot of problems regarding toric varieties, and what we do is we use the algebraic geometric structure to study problems. So let me go a little bit deeper into one problem which the community has studied in depth, and is the following: when does the maximum likelihood estimation, when does the maximum likelihood estimator of a statistical model admits a closed form expression in terms of rational functions? Okay, so imagine the independence model of two random binary variables. You can write the MLE of this model like explicitly as polynomials. And I mean, the models we study are in general toric varieties, or more general discrete models that are algebraic varieties. And the punchline here is that we want to classify models that have this property. Okay, and what we do is, in this setting, we associate a way to measure the complexity of the maximum likelihood estimation problem, but in a way that makes sense for algebraic geometry. This is what it's called the maximum likelihood degree of the statistical model. And maybe you can imagine that if the maximum likelihood degree of the model is 1, that means that the model has a closed form expression for the maximum likelihood estimate. Okay, and then how has this developed through the years? Well, let me start with the work of Junher and Bernd Sternfels. Okay, Junher first. He gave a classification of the models that have maximum likelihood degree 1. Okay, so all the discrete statistical models that have closed form expression, this is using algebraic geometry. And then you can read more about his results and other results in likelihood geometry in this first reference that I have here. And the idea is that you associate invariants in algebraic geometry to solve this problem. Okay. Later we picked up on the work on Junhe, and what Junhe did was classify general algebraic varieties that have this property. Later we specialized these results a little bit more to the case of statistical models. In a subsequent work, for example, one of the theorems that I proved with collaborators is to give a classification of the two-dimensional toric varieties that have a closed form expression for their MLE. And you can, there are several open questions in this area. For example, one of the things that I like to study is, give a classification of all the toric varieties that have this property. And, this is evolving, still were people working on this. But this is not just restricted to discrete statistical models. The last two references that you see here are references that consider Gaussian models. So these are sets of covariance matrices that are defined by polynomial equations, and you want to understand when these models have a closed form expression for their MLE. And in the first work, they associate invariants of algebraic varieties, namely classes, and they use different divisors and classes and intersection theory to compute degrees of maximum likelihood degrees, and this in fact has some connection with semi-definite programming. And more recently, Carlos Amendola and co-authors gave characterization using differential equations of Gaussian models that have rational MLE. So this is just one, let's say, deep dive into one problem that we have been studying in algebraic statistics, but there are many more. Algebraic statistics has contributed to the study of many of the bullet points that I have here on the left. So, for example, tensor decomposition, study of conditional independent structures, graphical models, and at the top here, I put three books in algebraic statistics in case you want to know more about our field. We also have a journal called Algebraic Statistics, and we also have a community of people that get together and talk about these problems. So, for example, we had a workshop in Oberwolfach last December, and this upcoming fall, there's a semester program called Algebraic Statistics and Our Changing World in the Institute for Mathematical and Statistical Innovation in Chicago. And what I've explained here is that you can use algebraic geometry to solve problems in statistics, but the tools that we use and develop are applicable to many more problems in computational geometry and optimization. So in the session that we'll have here, several talks will go into that area. So what I want to say is that the tools of algebraic geometry are there to solve problems beyond statistics. And this, I wanted to highlight a conference that happened this summer, which is SIAM Conference in Applied Algebraic Geometry. In this community, we basically use all these tools to solve problems more generally in the sciences. And I want to finish this talk by leaving you with Frank Nielsen's curated list of books in algebraic statistics, in case you are more interested in references. And yeah, thank you very much.